Response surface methodology, or RSM, is a collection of mathematical and statistical techniques useful for the modeling and analysis of problems in which a response of interest is influenced by several variables, and the objective is to optimize this response. This slide shows an experimental region where the response increases as the color becomes darker. Let's imagine we have designed our first experiment to understand the system's behavior. The final objective is to maximize the response. As we didn't know anything about the system when we began to study, the first design, the starting operation conditions, are far from the optimum. As the contour lines in this region have little curvature, we can describe the behavior by a linear model. Although the linear model does not show the maximum response, it shows the path of improvement that, if followed, can lead the experiment to the vicinity of the optimum operation conditions. In this region, the behavior of the response is not linear anymore, so we must have a quadratic model to describe it and locate the point of the maximum response. The process of following the path of improvement is called the method of the steepest ascent. To simplify the procedure, let's go back to the example we have just solved in the previous video. A team of researchers is performing experiments to maximize the yield of a chemical reaction. Their first design, time between 30 and 40 minutes, and temperature between 150 and 160 degrees Celsius, showed yield around 40%. The output of the RSM function shows the table with the regression coefficients, the analysis of variance of the model, both of them we have already discussed, and the direction of the steepest ascent. Looking at the contour plot, the direction of the steepest ascent is perpendicular to the contour lines. It indicates the direction of the maximum increase in the response. The information in the RSM output tells us the relative variation between the two factors being studied. For each 4.6 minutes of increase in time, we should increase the temperature by 1.9 degrees. The mathematical form is delta temperature equal to 1.9 divided by 4.6 times delta time. For instance, if we decide that we will increase the time by 10 minutes in our next test, the temperature should be increased by 4 degrees. Let's do it. Starting from the central point, our next experimental conditions are 45 minutes and 159 degrees Celsius. Running the test, the resulting yield was 42.9%, higher than the starting point, 40.5%. So let's continue following the steepest ascent. The next experimental conditions will be 55 minutes and 163 degrees. The resulting yield is 49.7, again higher than the previous one. It seems that we are indeed on the right path. Then let's continue and test the conditions 65 minutes and 167 degrees Celsius. The result shows the yield continues to increase. So, still following the steepest ascent, the next test, 75 minutes and 171 degrees Celsius, results in a yield of 70.4%. The next test, 85 minutes and 175 degrees Celsius, shows a yield of 80.3%, still increasing. But the next one, 95 minutes and 179 degrees Celsius, results in a yield of 75.1%, lower than the result of the previous conditions. It seems that the conditions around 85 minutes and 175 degrees Celsius are in the experimental space of the highest yield. Let's check this assumption by building an experimental design around this point. We can use the conditions of 85 minutes and 175 degrees Celsius as the central point. The ranges of the time and temperature for the design can be chosen freely. Let's go with the same range used in the first design, 10 minutes and 10 degrees Celsius. The temperature will range for 170 to 180 degrees Celsius and the reaction time from 80 to 90 minutes. The design was run as a single replicate in the factorial points and with 5 replicates at the central point. The relationship between the coded and the natural variables are also given in the slide. Let's analyze the data together. Please download the data and the R code files, and let's jump to R.